Hey everyone, welcome back to Linear Algebra. This will be lecture 5 of the course, and in this section we're going to shift gears slightly and start talking about linear systems. So we'll have a collection of lectures here that are going to revolve around linear systems. And in this first one, this first lecture of the section, we're going to define what we mean by a linear system, and we'll take a look at kind of the introductory approach to solving a linear system, and that would be Gaussian elimination. Okay, so let's go ahead and get started. And we'll call this section 2.1, Solving Linear Systems with Gaussian Elimination. Okay. And so we need to start by defining what we mean by a linear system. And a linear system, turns out, is nothing more than a collection of linear equations. So let's talk through what do we mean by a linear equation. Okay, so linear, so I'm going to make that legible here. A linear equation, okay, is an equation involving one or more variables in which only the operations of, we're going to limit the range of operations that can be done in an equation if it's linear, in which only the operations of summing terms. Okay, so an equation will have terms, and in this case we'll be summing them, and multiplication by real numbers. Okay, so a linear equation is an equation involving one or more variables in which only the operations of summing terms and multiplication by real numbers is allowed. Okay, and so these are very familiar equations. We've seen these for a very long time. Here are some examples. 6x minus 3y equals 4. Okay, so you've got multiplication by real numbers. You've got summing of terms. So I think it's more noteworthy what you don't have. What don't we have here? Well, we don't have exponents that are exponents other than 1. Right? We don't have things like square roots, which would be like rational exponents. We don't have variables in the denominator, right? So we don't have negative exponents, really. So I think one of the maybe the key way to characterize a linear equation is that the exponent on the variables is always 1. Okay, here's an example using the familiar xy, but as we move into this section, we'll be shifting, not exclusively, but predominantly, to a notation of variables that are x's with subscripts. So 8x1 plus 3x2 minus 4x3 equals negative 20 would be an example. All right, so this is a linear equation in 3 variables. Okay, and this is a linear equation in 2 variables. Okay, so we're familiar with linear equations. In fact, a linear equation, if you graph or plot the solution set for a linear equation, we know that it looks like a line. In 2D space, it's a line, right, in the plane. Okay, and so we're familiar with the way these look, particularly in the 2-dimensional case. So let's talk about what do we mean by a system of linear equations. Well, a system of linear equations that emerges when you consider 2 or more linear equations in the same variable at the same time. So a system of linear equations emerges when you consider a collection of 2 or more linear equations in the same variable at the same time. Okay. So a system of linear equations emerges when we consider two or more linear equations in the same variables at the same time. All right, so some examples. Let's see an example. Okay, so a simple one, right? Just 3x plus 2y equals 10, and 2x minus y equals -4. That would be a system of two equations in two variables. Okay, so this is a first example. Right, this is basically going to be a couple of lines in the plane, right? Here's another example. 3x1 minus 2x2 minus 5x3 equals 4. 2x1 plus 4x2 minus x3 equals 2. 6x1 minus 4x2 minus 10x3 equals 8. And maybe we'll put one more on here. -4x1 plus 8x2 plus 9x3 equals -6. Okay, so here's another system. This is a system of four equations, four linear equations in three variables. Okay. Now, usually when we write a system like in this kind of notation where we like literally list the equations, it's common to put a brace around the system like this, just to indicate that this is in fact being thought of as a system of linear equations, a system of equations. Okay, so this is an example of a system of linear equations. Okay, and so what do we mean when we say, when we talk about solving a system of linear equations? Well, let's think about what it means when we say we have a solution to a particular equation, like one equation. Like a solution to an equation, let's say a solution to this equation here is x1, x2, x3 equals 4, -1, 2. Now, if you take this triple and you plug it in x1, x2, x3, you'll find that this equation is satisfied by these three values of x1, x2, x3. Now, it turns out that this is a solution to the entire system, and what that means is that I can plug this triple into any of these equations and it will satisfy any of them, right? So maybe we should just try this. Let's plug in this value for the top equation. So 3 times 4 minus 2 times -1 minus 5 times 2 equals 4. Okay, let's see here. So I've got 12 plus 2 minus 10 equals 4. Okay, and so I can see that that means over here I've got 14 minus 10, so I've got 4 equals 4. Check. Okay, what about if we plug that same triple into the second equation? I would have 2 times 4 plus 4 times -1 minus 2 equals 2. Okay, so let's see if this one works out. So I get 8 minus 4 minus 2 equals 2, and so that's 8 minus 6, so that gives me 2 equals 2. Check. Right, so there it satisfies. This is equation 1, and this was equation 2, right? And so you can see that the same solution satisfies both of these equations, and indeed if you were to try these other two as well, you would see that this solution satisfies all four of these. Okay. And so that's why we say that this is a solution to this system. So this particular triple here is a solution to this system of equations. All right. Now this is an example of a particular solution, because it turns out that there are other solutions. So 4, -1, 2 is a particular solution to this system. Okay, it's a particular solution to this system. There are others. Another example would be this solution. Another example would be this guy here, -3/2, 3/4, and -2. All right, so if you take this this triple here and plug it into these same equations, you'll find that indeed this is another solution. Okay. Now it turns out for this particular system there are infinitely many solutions. Okay, so it turns out there are infinitely many solutions to this particular system. Okay. Now that's not always going to be the case, but in this case it is. Okay. Very good. Let's go ahead and formally define what we mean by a system and knock out some kind of formal description of what we mean by the solution set here. Okay, so definition. Okay. A system of m linear equations in n variables. Okay. And then we'll just kind of put a comma there, and let's actually like write this out a little bit. a11 x1 plus a12 x2 plus ... plus a1n xn equals b1. Okay, so this is the first equation in the system. So notice you've got 1, 2, ... n terms, right? Because there's n different variables. Okay, and the second equation could be written like this: a21 x1 plus a22 x2 plus ... plus a2n xn equals b2. Okay. So again, you've got the same number of variables, x1s, x2s, xn's. Okay, and then this would go on for how many rows would I have in this system? How many equations? M, right? So m linear equations, n variables, and so I would have down here a m1 x1 plus a m2 x2 plus ... plus a mn xn equals bm. Okay. Right, and so this is sort of the blueprint for a system of linear equations. So this particular system has m equations and n variables. Okay, so a system of m linear equations in n variables is a collection of, as we said, m equations, each containing a linear combination of the same key n variables, and then summing to a scalar. Okay, and so here we can see that this is indeed a linear combination of n variables summing to a scalar. Same for all of these, right? All right, and so that's the definition of a linear system. It's a collection of equations, each containing a linear combination of the same n variables summing to a scalar. Okay, and then talk about solutions. A particular solution is an n tuple, right? This has we're talking about a system with m equations and n variables, so your solution, particular solutions, are going to have n values, so it's going to be an n tuple. So a particular solution is an n tuple, and we'll say S1, S2, dot, 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 Sn, that satisfies each of the m equations in the system. Okay, so that's a particular solution. And a complete solution set a complete solution set is the collection of all particular solutions. All right. Okay, so a complete solution set is a collection of all particular solutions. So, and we'll talk about this in more detail in a moment, but there are going to be different types of solutions for a given system, right? So we'll get into that in a moment. One of the types is to have a particular solution or multiple particular solutions. And so in the case of multiples, you'll need some way to denote the complete solution set. So we'll get into that in a moment, but let's continue down this road of talking about the system itself before we get too deep into the solutions. So you may have noticed as we were looking at this notation that the coefficients here, a11, a12, a1n, the notation that's being used here closely resembles the notation of the entries of a matrix. And indeed, that's not by accident, right? So the coefficients of x1 through xn can easily be collected together and inserted into an equation, into a matrix. And so in this definition, let's talk this through. In this definition, the coefficients of x1, x2, dot, 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 xn can be collected together into an m by n matrix. Okay, they can be collected together into an m by n matrix called the coefficient matrix. The coefficient matrix, right? And so you can see that it must be m by n, right? Because let's say we insert equation 1's coefficients into the top row, and then equation 2's go into row 2, and then equation m goes into row m. Well, there are going to be m rows, right? And then how many columns? Well, there'll be a column for the coefficient of x1, a column for the coefficients of x2, dot, 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 a column for the coefficients of xn. Okay, so an m by n matrix. And so it would look like this. a11, a12, dot, 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 a1n, a21, a22, dot, 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 a2n, right? And then so on, am1, am2, dot, 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 amn, right? And so this is just a matrix that disregards the variables, disregards the constants, scalars, and just loads into it the coefficients, right? And so you can tell which variables go with which coefficients based on the position. So these are all the variables here for the x1. I'm sorry, these are all the coefficients for the x1 variable. These are all the coefficients for the x2 variable, and so on, based purely on their position in the matrix. Similarly, this top row represents equation 1. The second row represents equation 2, and so on. Right, so which coefficient goes with what is retained, that information is retained based on the position of the coefficient in the matrix. Okay, and so there's our coefficient matrix. All right. Let's take this a little bit further. I'm going to rewrite our coefficient matrix A. So A11, A12, dot, 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 A1n, A21, A22, dot, 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 A2n, AM1, AM2, dot, 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 AMN. Okay, so there's our coefficient matrix. So what we can also do, we can also let X be X1, X2, dot, 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 Xn. So this is an n by 1 matrix. And B be the B1, B2, dot, 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 Bm, m by 1 matrix. And when we do that, these three matrices can be used to represent this system of ours. So the linear system is equivalent to the matrix equation AX equals B. Okay, AX equals B. So let's make sure we understand this. To kind of see this, let's make our system a little bit smaller just for convenience sake, and then when we go through the smaller example, you'll see how this applies to any example. But let's make our system a little bit smaller here. So to see this, let's consider a smaller system. Okay, still a general system, but let's consider A11 x1 plus A12 x2 equals B1, A21 x1 plus A22 x2 equals B2. So like a system of two linear equations in two variables. So in this example, our coefficient matrix would be A11, A12, A21, A22. Okay. X here would just be x1, x2, and B would be B1, B2. Okay. And so when we say AX equals B, what do we mean? We mean A11, A12, A21, A22 times x1, x2. That's matrix multiplication, remember. Okay, so what happens when we do this multiplication? Well, remember the multiplication. So if we want so this is, first of all, this is a 2 by 2 multiplied against a 2 by 1. And so let's remember what happens here. So the multiplication is defined because the number of columns of the A matrix is equal to the number of rows of the X matrix. And the resulting matrix, the matrix that is a result of this multiplication, is going to be 2 by 1, right? Because of these guys here, right? And so let's go through this multiplication. So you'd have A11 times X1, right? This is the dot product here. So this A11 times X1, and then A12 times X2. Sorry, A12 times X2, right? So just the dot product. You're dotting this vector here with this vector here. Okay, and then you do the same thing with the next row down. So this gives us the A11, or sorry, the AX 1 value. The next one would be got by doing this one time dotted with this one. So you get A21 x1 plus A22 x2, right? So you get this matrix. And this is indeed 2 rows, 1 column, right? Okay. And we're saying that A times X, which is what we just multiplied together here, is equal to B. And so B is B1, B2. Okay, and that's indeed the case, right? So now consider what we're basically saying is that the 1, entry is equal to B1. So that's A11 x1 plus A12 x2 equals B1. Well, that's just the first equation in the system, isn't it? That's just the first equation in the system. And then we're saying that the A21 entry is equal to B2, right? And that's just going to be this guy, A21 x1 plus A22 x2 equals B2, right? And that's just the second equation in the system. All right. So you can see that using this coefficient matrix idea allows us to represent a system of linear equations as a matrix equation. Okay. All right. Very good. And so I guess kind of another way to say this would be that this is the left-hand side of the system, right? Namely this part here. And this is the right-hand side of the system, right, namely that part there. Okay. All right. So this is the idea behind the matrix equation, AX equals B, and how it relates to the system. Now, there's an alternative method which is convenient, which will help kind of lead us into our Gaussian elimination. All right. So an alternative approach to representing this, to representing the system, is to form what's called an augmented matrix. Okay, so you start with the coefficient matrix. So A11, A12, dot, 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 A1n, A21, A22, dot, 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 A2n, and then AM1, AM2, dot, 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 AMN. Right, you start with the coefficient matrix, but then we insert into the coefficient matrix the scalars, right? The scalars that each of the equations sum to. So B1, B2, dot, 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 Bm. Okay. Right, and so this is called an augmented matrix because it starts with this regular coefficient matrix, and then we add to it, we augment it with the scalar matrix, the B matrix. Okay, and this is frequently denoted as A, B, like this, with this kind of vertical line indicating this is an augmented matrix. And so you can kind of see this, that basically in this case each row represents one equation in the system. Right, so clearly this is equation 1, right? This is equation 2. Okay. Each of the columns still represent the variables. This is x1s, these are the x2s, these are the xn's. Right, this is obviously equation m. Okay, and so you can see that all of the information as to what these numbers represent, what variables and equations they go with, is all still retained by the position of the numbers. Okay, and so A augmented with B is really the coefficient matrix together with the scalar matrix. Okay. All right. Okay, let's do an example where we take a system and we sort of insert it into this structure, this augmented matrix structure. Let's do an example of that quick. So let's consider this system 4w minus 2x plus y minus 3z equals 5. That's the first equation. And the second equation is 3w plus x plus 5z equals 12, right? So something like this. Okay. Let's write it both ways. Let's create both the ax equals b equation, matrix equation, and then let's also develop the augmented matrix. So the coefficient matrix, we'll start with that. And we'll just kind of think of it as w, x, y, z in terms of columns. Okay. Now technically the order really doesn't matter as long as you know what the order is and as long as your x matrix retains the same order. But here we can see that we'll have a 4, -2, 1, -3, and then we'll have a 3, a 1, a 0 for the y variable in equation 2, and a 5. Okay, and so here is my coefficient matrix. X is going to be wxyz, wxyz, so you just want to make sure you use that same order. And then, of course, b is going to be 5 and 12. Okay, and so ax in this case, let's write this out. It's going to be 4, -2, 1, -3, 3, 1, 0, 5 times the x matrix, w, x, y, z. Now what happens when we multiply these together? Let's make sure we can see this. So you're going to dot the first row with the first column, and so you get 4w minus 2x plus y minus 3z. Right, that's the first row with the first column. And then you're going to do the second row with the first column, and it's going to be 3w plus x plus 0y plus 5z, right? And so that's ax. And then clearly that's equal to b, right? Because this is the first equation, and it's going to equal 5. If you look back at the system, it's the same deal. This is the second equation, it equals 12. You can see that in the original system as well. Okay, so this is the ax equals b matrix equation. And then let's go ahead and develop the augmented matrix. Well, it's just the coefficient matrix connected to the scalar matrix. And so it's going to be 4, -2, 1, -3, and then 3, 1, 0, 5. So that's the scalar side. And then that's the coefficient side. The scalar side is going to have just a 5 and a 12, right? Like so. And so that's the augmented matrix. All right. Okay, perfect, perfect. And so this is going to be the setup that we'll use when we are trying to solve these systems using Gaussian elimination. Okay. Now, before we get into how Gaussian elimination works, we need to talk through what the solutions to a system can, what kind of forms they can take. Okay. And so there's really three options. There's 3 possibilities to the size of the solution set. So there's 3 possibilities to the size of the solution set. Okay. So the first option is there can be a single solution. Okay. The second option is that, so the first option, meaning a single solution, means that there's literally one ordered triple or ordered n-tuple that satisfies all of the equations. Just one. The second option is there can be an infinite number of solutions. And then the third option is that, well, what do you guess, right? It's either one, infinitely many, or none, no solutions. Okay, a single solution, an infinite number of solutions, or no solution. Those are the three options. And to kind of help illustrate this idea, we can take this sort of simplified system of two equations and two variables, which is kind of going to correspond to the sort of the familiar xy plane. Okay, and so let's take a look at the example where you have a single solution. Okay, like a single solution. Well, a single solution, a system that has a single solution would be like 4x minus 3y equals 0, and 2x plus 3y equals 18, right? And so we'll just call this equation A and equation B. Okay, now if I were to plot these in the xy plane, then one of them is going to go through 0, 0 down here, and it's going to go through 1, 2, 3, 1, 2, 3, 4. It's going to cross through this point as well, right? And that's going to actually be the A equation, right? So this guy here. So if you just kind of look at this, you can see that this is obviously going to have a y-intercept of 0, right? If you could convert this to slope-intercept form and quickly plot these, right? And you'd see that this first one looks like this. The second one is going to have, and it's going to obviously have a positive slope, right? Because you'll get the negative 4x over here, and then you divide by negative 3, and it becomes positive, right? So you'll have a positive slope. The other one is going to have a negative slope, and it's going to go through, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to cross through here. It's also going to cut through here. And it's going to have, let's see, 1, 2, 3, 4, 5, 6. It's going to have a slope intercept of 6. Okay, and so it's going to kind of cut up through here. Okay, sorry, let me twist this a little bit. There we go. And so this would be equation B. And so in this example, the two lines of the system are going to intersect at exactly one point. So the lines intersect at exactly one point, right? Namely this guy here. This is 3, 4. Okay, and so 3, 4 is going to be the unique solution to this system. Right? There's just going to be one solution. Okay, and so 3, 4 is the single unique solution to the system, right? And now logically that should make sense because there's only one point that's going to simultaneously be on both lines, right? A solution to either of the equations has to be a point on the line, and if these are lines in the plane and they intersect at only one point, clearly that one point is going to be the solution to the system, right? And so this is the case where there's a single solution. Okay. What happens when there are an infinite number of solutions? Well, in those cases, okay, let's take a look at that. An infinite number of solutions. Again, we'll just kind of operate in the xy plane. And an example solution like that would be 4x, or sorry, an example system would be 4x minus 6y equals 10, and 6x minus 9y equals 15. Okay, Now, if you look closely at these lines, what you'll notice is that, well, first let's plot. Let's plot one of them. Okay, let's plot. Oh, actually, I need to come down a little bit here. Let's plot this first line, right? And so this guy is going to intersect at 5 halves, right? So that's about 2.5. So 5 halves 0. Okay, the first line will go through there, and then negative, and then 0, comma, negative 5/3. And so you could just do the algebra here to quickly see this, but I'm just, in the interest of time, trying to draw this quickly for you. Okay, so maybe this is line A. Right, you can just do the algebra, just put that equation into slope-intercept form, and you can plot these things really quickly. Okay, now as soon as you go to line B and you try to do the same exercise, what you're going to discover is that in fact these are really the same line. So here, comma, the two given lines are really the same line. So they're really the same line. One's a multiple of the other, right? And so you can see this really quickly. Just notice that if I take my first line, or my first equation, 4x minus 6y equals 10, and I multiply both sides by 3 halves. So if I go like this, and what happens? Well, over here I get 12 over 2x, and then I get minus 18 over 2y, and that's going to be equal to 30 over 2. Now when I simplify this down, what happens? I get 12 over 2, that's a 6x, and this is minus 9y equals 15. Okay, so this is exactly the same as the second equation. Okay, so we started with 4x minus 6y equals 10, 4x minus 6y equals 10, multiplied the whole thing by 3 halves, and now look, lickety split, I've got equation 2. Right, so basically the moral of the story here is that when you have infinite solutions, essentially you're talking about the same line. And so every point on line A is the same as every point on line B. Hence, there are an infinite number of solutions to the system. Okay, so that's what happens in case 2, where you have an infinite number of solutions, basically talking about the same line. Okay, and then line 3, or option 3, is to have no solution. Okay, so no solution. An example of that would be 2x plus y equals 3, and 2x plus y equals 1. Okay, so that's a system. You can kind of look at this and you might be able to see, that there's something funny here, because the left-hand side of the equation is identical, the right-hand side is the only difference. And if you know what that right-hand side represents in this case, that's going to be the y-intercept. So you basically got the same line shifted up, right? So let's see what this would look like. Okay, so the one goes through, so this one goes through 0, 3, and then the other one goes through 0, 1. Right, and they both have the exact same, sorry, I'm going to just draw it. They both have the exact same slope, right? And so they're parallel, aren't they? So these lines are parallel. Okay, so they're parallel, but they're not equal, right? The previous example, of course, that these two lines up here were parallel as well, but they were identical, actually. They were parallel. They had the same intercepts. Here, these two are parallel, but not equal. And so what do we know about parallel lines in the plane? Well, they never intersect. Right, so the fact that they're parallel means they never intersect, and of course that means they have no system solution. Okay, they have there's no solution to this system. Okay, very good. And so those are kind of some good examples of what we mean by each of these different types. Okay, and so we have some a little bit more terminology here. A system that has at least one solution is said to be consistent. A system with one or more solutions is said to be consistent. Okay, and so that's going to, obviously, there's just two cases. You're going to have one. When I say more, I mean or infinitely many. One or infinitely many solutions. Those systems are called consistent, and a system with no solutions is said to be obviously inconsistent. Okay, so consistent, inconsistent. It's not just some terminology that people use. Okay, so I think, let's see here. I think we'll talk quickly about kind of the overview of Gaussian elimination, and then we'll split the video in two for some of the examples, because this will get along. We have to do a number of examples to kind of help make this clear. So there are many ways to solve a system. We're going to start with what's called Gaussian elimination. And this is obviously named after Carl Friedrich Gauss, the famous mathematician. So the basic idea with Gaussian elimination, so you're going to start with a augmented matrix. So 2, 10, 3, 10, 1, 5. I'm just putting in numbers here. 1, 5, 6, 9, 4, 0, 3, 8, we'll say. So you start with some augmented matrix like this. And then what you want to do, it's kind of like a traditional sort of solving of equations in algebra. You want to start with a Gaussian, you want to start with an augmented matrix, and you want to do some things to it. I know what those things are we'll get into in a moment, but you want to do some things to it until the system is kind of replaced, the coefficients are replaced with simpler numbers that make the solution more apparent. Okay, so something like this, right? So the idea is you start with just taking the system itself and coding it into an augmented matrix like this. Then you're going to do some things to it, and of course what those things are we'll get into in great detail, until the system, the augmented matrix, looks a particular way. And once it looks a particular way, you're going to be able to more or less read off the solution to the system. Okay. And so it's similar to what you're used to doing with solving algebraic equations. You start with an equation, right, in normal algebra. Right, in normal algebra, you maybe start with an equation. What do? Well, you do a bunch of junk to it. Right, you may remember it's called algebraic manipulation, right? Add 5 to both sides, divide both sides by 3, da 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 da. You kind of go through this this ordeal of algebraic manipulations, and what you arrive at in the end. Let's not make this. Well, that's fine. What you arrive at in the end is x equals something, right? So you start with something convoluted, you do a bunch of algebraic moves to it, and you simplify the system, or sorry, you simplify the equation until the answer is readily apparent. X equals some number in this case. This is analogous to that operation. You start with a matrix, you do a bunch of matrix operations to it until it looks a particular way, and when it looks a particular way, you'll be able to read the solution directly off the matrix. Okay. And so, obviously, the point, the hard part of Gaussian elimination is all the stuff here. This is like clearly the hard part. Same with regular algebra. The hard part is all of the algebra. And so, let's talk through what we mean by this hard part. Well, we can spend a moment on this though. So the goal is to get the matrix into a particular form, and Gaussian elimination doesn't go quite this far, but let's just use this as a starting point for talking about this method overall. So you start with this matrix of numbers, you do a bunch of stuff to it until it looks something like this, right? And if this were what your matrix looked like, this of course is your x1, your x2, and your x3 columns, right? And so what is this top row telling you? This says that 1x1 is equal to A. And this second row is telling you that 1x2 is equal to B. And this third row is telling you that 1x3 is equal to C. Right, now assuming the solution sets between this starting matrix and this final matrix are the same, which is of course what this hard part here has to retain. Same as down here, you're continuously turning this equation into an equivalent equation, another equivalent equation, another equivalent equation. You're doing the same thing here. You're taking this augmented matrix and converting it, step by step into an equivalent augmented matrix. Okay, and so what does this tell you when you do this? Well, you can see that your solution x1, x2, x3 is equal to A, B, and C, right? You can just read them right off, right? A, B, C. So that's how, that's kind of the sort of high-level view of what's going to be happening here. Now, of course, the devil's in the details, and so this part here, how do we step-by-step convert an augmented matrix while retaining all of the solutions is sort of the tricky part. And so that's where the idea of row operations come in. All right, and this is a short list of operations that can be done on a matrix that doesn't change the solution set of the underlying system. Okay, and so these are actually fairly simple rules, and after you practice them a few times, it's sort of startling how easy this is compared to the kind of algebra you're maybe used to. Okay, so there's three of them. There's just three rules, three row operations. The first one is you can multiply a row by a non-zero scalar. You can multiply a row by a non-zero scalar. Okay, so any row in the matrix, I can multiply by any real number, non-zero real number. Okay, without changing the solution set of the resulting matrix, right? So my starting matrix and my resulting matrix after this scalar operation on a row has the same solution set. Okay, what else can we do? That's step one. The second one is I can add a scalar multiple of one row to another row. Okay, and we'll see some examples of each of these in a second. But basically this just says, hey, if I what I can do is I can take row 1, multiply it times 10, and then add that new row 1, 10 times row 1. I can add it to row 2. Okay, and replace row 2 with that sum. Okay, so this is the first one is very obviously easy. The second one is the most complex of the three. The third one is by far the easiest. You simply switch the position of two rows. I can switch the position of two rows in the matrix. Okay, doesn't get much easier than that. You can literally just swap the rows out. Okay. All right. Let's do an example. Let's do an example of each one of these just to make sure we're very crystal clear on how this works. So let's start with row operation number 1. Example, row op number 1. Okay. And so this says I can multiply a row by a non-zero scalar. So let's crank out a matrix here. So 2, 3, 4, 5, 6, 7, and then 4 and 10. Okay, so let's say this is my augmented matrix. What this row operation 1 says is I can multiply a row of the matrix by a non-zero scalar. So let's say I want to multiply row 1 by the number 2. Well, then that means this matrix here is equivalent to 4, 6, 8, 8. Okay, so you can see that. So basically row 2 is unchanged, 5, 6, 7, 10, 5, 6, 7, 10, but row 1 is now twice row 2. Okay, and so doing this operation preserves the solution set. Okay, so you can look at this and say, well, these augmented matrices are now different, the entries are different, but what this means is that whatever the solution set is to this one, the same solution set is going to be here, right? These row operations have a certain nature. They do not impact the solution set. They certainly change the numbers, but they don't impact the solution set. Okay. So that's an example of row operation number 1. Let's talk about row operation number 2. Okay, row operation number 2. Okay, and so this one, remember it says add a scalar multiple of one row to another row. Add a scalar multiple of one row to another row. Okay, so that's the row op 2. Now, this is by far the most challenging of the 3 row operation. It's not rocket science or anything. It's not terribly difficult, but it is the one that requires, I guess, the most kind of like mental math, right? So let's start with a matrix here, and we'll say 2, we'll just go with the same one, 2, 3, 4, 4, 5, 6, 7, 10. And let's say what we want to do here is, well, actually, hold on a sec. I don't want to use that one. I'm gonna need more space for this too. Let me go to the next page here. So this will be our example row op number 2. Okay. So I want a different matrix. I was looking at the wrong one here. So let's do this. 1, 2, 3, 4, 5, 6, 7, 8. It doesn't matter. I want a 1 for this particular operation. Okay, so here what I'm going to do is I'm going to take, here we will take -5 times row 1. Okay, we're going to take -5 times row 1, and we're going to add it to row 2. Okay. And that sum will become the new row 2. Okay. So we're going to take, here we will take -5 times row 1 and add it to row 2. And so you can notate this however you want. There's like a lot of different ways to notate. I kind of like to just keep it simple, but of course I have had more practice here. The way I do it is I say, okay, I'm going to do this. I'm going to take -5, and so I put the -5 on the row that I'm going to multiply it by, and then I indicate which row I'm going to add it to by this little arrow. Right, so this literally means, to me, this literally means I'm going to take -5 times this row, I'm going to add it to this row. I'm going to take -5 times row 1 and add it to row 2. I've also seen people go like this. People will use more elaborate notation. You could do something like this, like -5 times row 1 plus row 2 into row 2. Okay. I mean, so there's different ways to notate this. I think, you know, different textbooks will have different criteria, different standards. This is probably the most common approach, like to use R1, R2 as your row indicators, and then just kind of create a little arrow equation like this. So this literally says take -5 times the entire row 1, add that to row 2, and then that, whatever that is, becomes your new row 2. Okay, so let's go ahead and go through this. Okay, so with this row operation, the only row that's going to change is row 2. So 1, 2, 3, 4 stays the same. We got to replace row 2. So here's how it's going to go. We're going to say -5 times 1 is -5, plus 5 is 0. Okay, right? -5 times 2 is -10. -10 plus 6 is -4. Okay, and then you would say -5 times 3 is -15. -15 plus 7 is -8. And then -5 times 4 is -20. -20 plus 8 is -12. Okay, and so that's kind of what we've done here, right? So that would be the completion of this row operation. We've taken row 1, multiplied it times the scalar -5, added that multiple of row 1 to row 2, and that became our new row 2. So -5 times 1 is -5, plus 5 is 0. -5 times 2 is -10, plus 6 is -4. -5 times 3 is -15, plus 7 is -8. Okay, so another way to kind of think about this, you know, it maybe a side if you know, when you're starting out, maybe a side calculation is useful. Start by doing the multiple here. So -5 times 1, 2, 3, 4. So you get -5, -10, -15, -20. So that's just the -5 times row 1. And then I got to add to that row 2. So 5, 6, 7, 8. When I do that, I get -5 plus 5 is 0. -10 plus 6 is -4. -15 plus 7, -8. And then -20 plus 8 is -12. And so you can see these guys here are what I loaded in for row 2. Okay. And so that's row operation type number 2. Again, this is definitely the most, of the 3, this is the one that requires the most like kind of mental math. But there are lots of ways you can calculate things on the side like this. I think this is a good idea. Some people really like to use the row operation notation. What's common is people will put the row operation notation in between the matrices. You know, this little squiggle here, by the way, this little tilde, that is meant to mean equivalent, not equal, equivalent, right? And in the context here, it just means they have equivalent solutions. Okay, and then let's just do a quick example of row operation number 3. Okay, so row operation number 3, remember, was, what was the exact wording? Switch the positions of 2 rows in the matrix. Okay, we can switch the position of 2 rows, right? And so this is just a simple thing. 1, 2, 3, 4, 5, 6, 7, 8. If this is my augmented matrix, then I can change the order of the rows. So I could put row 2 first, for example. Now that one should be obvious that that doesn't impact your solution set. I mean, clearly, if your system of linear equations is written out and you have 2 equations, it doesn't matter which one's on top or which one's on the bottom, right? And that's all this is saying. So this one is very straightforward. Okay. All right, let's go ahead and I'm going to stop the video here, and then we'll pick up with a part B for this section, where we'll get a little further into the strategy of using these row operations, and then we'll do a handful of examples as well to make sure we're clear on it. All right, see you in a moment.